Here we have a depiction of an object, the round circle representing the object, which is released from rest, accelerates at 9.8 meters per second squared in the downward direction, that is, accelerates freely under the influence of gravity, and falls for a time delta t equals 1.7 seconds after its release. We want to know what the velocity of the object is after this time interval is passed. And of course, this is a fairly straightforward problem. Using definitions of acceleration and velocity, we see that the change in velocity is a product of the acceleration, which is the rate of change of velocity, and the time interval. And we multiply the acceleration by the time interval, we get a change in velocity of 1.67 meters per second. Now we can answer a couple more questions. This is the only question that's really asked in problem 12. The problem 13 goes on to ask things about distance, so we're going to continue and talk about that. So the final velocity, of course, will then be the initial plus the acceleration times delta t, 0 plus 1.67 meters per second, or just the 1.67 meter per second change in velocity since we started from rest. The displacement is going to be the product of the average velocity and delta t. Since the acceleration is uniform, the average velocity will be the average of initial and final velocities, and that's going to be multiplied by the 1.7 second time interval. We complete the calculation easily enough and determine that the object is going to fall a distance of 1.4 meters, 1.42 meters in 1.7 seconds. And there's a serious error in this problem that I'm going to have to fix right in front of you here. My decimals are wrong. This is 16.7 meters per second, not 1.67. So that's going to move the decimal here, it's going to move the decimal here, and it's going to move the decimal here, and it's going to move the decimal here. So that this will be 16.7 meters per second. This will be 8.4 meters per second average velocity and 14.2 meters. In 1.7 seconds, we fall a lot further than 1.42 meters. Okay? The procedure is correct, but the numbers were wrong there at first. Okay, we fixed them. So in general now, the final velocity you're going to have in a situation like this will be plus or minus the square root of this expression here, the initial velocity squared plus 2a delta s, and that just comes from the third equation of motion. And that's one way that you might calculate final velocity if you know initial velocity, acceleration, and displacement. Alternatively, if you know initial velocity and delta t, you can just calculate the final velocity using v0 plus a delta t, which is what we did in the previous example. The displacement delta s in either case will be the average velocity times delta t, or if you prefer, you can use v0 delta t plus 1/2 a times delta t squared, which is another expression, of course, for the displacement.